Welcome everyone to what is the last lecture of this season. I'm delighted to say that it has gone, I think, very well. We've had a very good response to putting everything onto the Zoom platform, and it's given us the opportunity to leave a legacy after each talk and have the recordings there for a little while, so people who, for whatever reason, weren't able to make the evening have been able to catch up in their own time. So I think going forward, we're looking to perhaps have hopefully a little bit more hybrid of a season in future, with physical lectures where we can, but use the virtual opportunity to maybe go slightly further afield and bring in people from overseas or whatever, as long as the time differences allow. So we'll be putting next year's program together very soon, and if you have suggestions, things you've seen elsewhere, and you would like to share those with your fellow Edinburgh members, let me know and we'll begin to build those into the program. We've got COP26, of course, coming up at the end of this year, and so we'll be looking to reflect some of the themes in that, certainly in some of the autumn lectures. So anyway, without further ado, I'd like to introduce tonight's speaker, as Tom said, Dr. Heather Stewart, from the British Geological Survey. Heather, I think, joined BGS at the same time as I did, 2001. For me, it seems like a lifetime ago. I'm not sure what Heather feels, but Heather's a graduate of Glasgow University, joined BGS, as I say, in 2001 as a marine geologist. And it kind of looks like she's been getting her feet wet and going for a paddle ever since in all of that time. Very much involved in and very much driving various initiatives in seabed mapping for BGS and in collaboration with others. Everything from glacial geomorphology, which is where, as a sort of glutton for punishment, she's doing her PhD part-time at the same time as working for BGS, so nothing like a challenge. All the way from glacial geomorphology offshore in the kind of UK continental shelf areas to some of the deepest parts of our ocean basins across the world. And it's, I was having a quick look, let me just refresh my memory. If you go to Heather's publication list, she's got a wonderful paper there, a wonderful title at least, which says the 5 deeps, the location and depth of the deepest place in each of the world's oceans. Oh, what a title to be able to put into the literature, to have visited the deepest places in all of the 5 oceans. So I think that's a title we could all aspire to, that sort of thing. So going as deep as some people go high, I think that bodes very well for this evening's lecture. And Heather, I'll hand over to you in a second and introduce. The title I have is Exploring the Underworld, the Geomorphology and Sediments of Subduction Trenches. And Heather, over to you.
Okay, thanks very much. What a wonderful introduction. I'll just stop my video and then share my screen and we can crack on. So hopefully you can all see the main screen rather than the presenter view.
Yep, that's fine.
Excellent, okay. Yeah, so thanks very much for the introduction, and good evening, everybody. As Graham very kindly said, my regular stomping grounds are the waters round about the UK and the North Atlantic. But I have just been incredibly lucky over the last 7 years or so to have participated in a number of projects exploring the deepest reaches of our planet, including subduction zones, oceanic ridges, and so on. So I started doing that work for, I think it was about 2015. And since then, I've been on 8 or 9 expeditions to these ultra deep areas. And as Graham sort of mentioned, because of my experience working in these environments in 2018 and 2019, I was lucky enough to be expedition geologist for the 5 Deeps expedition, which will crop up later in my talk this evening. But I'm going to start by taking you on a whistle-stop tour of the deepest parts of our oceans. I'll touch a bit on the history of deep water exploration, past and present. I'll cherry pick some research highlights along the way. And but please just sit back, and I hope that you enjoy the journey that I'm going to take you on. And all things going well, there'll be time for some questions at the end. So, I mean, I know that this is old hat to some of you, but just to sort of go back in time a little bit, take a step back. By the 1850s, ships had been routinely crossing the Earth's oceans for over sort of 200 years. And although the coastlines of the main land masses had been surveyed, little was actually known about the sea beyond, a few tens of meters water depth. But as the sort of 19th century progressed, there was an increasing pressure to explore the ocean depths for science, military gain, and of course, commercial reasons, for example, laying cables for communication between Europe and America by telegraph could only be successfully achieved if you improve your knowledge of the shape and composition of the sea floor. But I mean, it wasn't until sort of 1773 that deep sounding expeditions began in earnest, with Lord Mulgrave setting off on an expedition towards the North Pole. And during that expedition, a maximum depth of 1,249 meters was sounded in the Arctic Ocean. And he published that in his tome that came out after that venture. But that record for the Arctic Ocean was subsequently beaten by Sir John Ross early in the 19th century, using a wire to deploy a deep sea clam in Baffin Bay, east of Greenland. And at that location, he measured a maximum depth of 1,920 meters, and he also took a sediment sample. So this technique of using a sort of sounding wire was, pretty much standard by this point. Many expeditions were taking long wires, with them usually marked every sort of 100 fathoms. And the time interval between each mark was noted until it was thought that the line had reached the bottom. So as you can imagine, it was quite an investment to take these long sounding wires with you. James Clark Ross took 6.5 kilometers of wire with him on his Erebus and Terror expeditions to Antarctica in the sort of mid 19th century. But it wasn't until the sort of Challenger expedition that explorers really started to grasp just how deep oceans might be. So if we turn our attention to the Challenger expedition, we're back in the sort of 1872 to 1876, and they covered nearly 70,000 nautical miles. They acquired soundings for water depth using 291 kilometers of Italian hemp as a sounding wire, and they collected seafloor, water, and biological samples on the way. So, but what was really surprising during that expedition was that completely by accident and unexpectedly, they recorded a depth of 8,230 meters in the Northwest Pacific, southwest of the Mariana Islands. And following the sort of naming traditions of the time, they called it Challenger Deep after their vessel. And that sounding was really the first measurement that implied, extraordinary depths in our oceans. And in 1895, Sir John Murray, who supervised publication of the scientific results from the expedition, he described the scientific work undertaken during that expedition as the greatest advance in knowledge of our planet since the celebrated discoveries of the 15th and 16th century. So that all sounds pretty cool. But I mean, Sir John Murray, he documented the first sort of systematic, can't speak tonight, good grief, the first systematic measurements of bathymetric depths. And he calculated the mean depth of the oceans and produced the first hypsometric curve. So, and that's essentially a graph that shows the proportion of land area that exists at various elevations by plotting relative area against relative height. So you really started to sort of have a look at what the shape of the ocean floor was and started to sort of try and think about reasons that it might be that way. So if we sort of skip forward a little bit to the turn of the 20th century, the Royal Navy were developing new methods to sound the deeps, including the Hydra and Bailey rods. And it was during an expedition to the South Pacific in 1893 to 94 on board HMS Penguin, hence the picture at the bottom there, that the greatest ocean depth record was sounded. And that was a depth of sort of 9,427 meters in the Kermadec Trench. And I'll come back to the Kermadec Trench in a little while. And so we're firmly now in the 20th century in the realm of the echo sounder. And these new echo sounder methods relied on bomb sounding. So in other words, somebody lobbed a half-pound block of TNT off the back of the boat to create a sound source. And you measure the time, you know, it's really basic. You measure the time it takes for that echo to travel from the source down through the water column, reflect off the seafloor, and then you receive it back on board the boat. And use that to determine the true water depth. And you know, you're getting more and more accuracy than just using your sounding line. And the German research vessel Meteor was the world's first expedition to make use of this newfangled technology for science. So in 1926, during an expedition to the South Atlantic, they used this sort of cutting edge technology to sound the deepest point in the South Sandwich Trench, and that was at 8,264 meters. We also on the right there have another example where the Danish Galathea expeditions in the 1950s, they also used this sort of early echo sounding technique to survey the Philippine Trench. And again, that was the first time that, that these really deep areas were starting to be resolved in any sort of detail. And, you know, you've got to remember that at this point, you know, the theory of plate tectonics was still in its infancy. It was still very controversial. So the fact that they've got these ultra deep areas in the ocean was a lot of interest, but also quite controversial. It caused an awful lot of arguments. So it wasn't until the 1950s that Bruce Hazing and Marie Tharp, that partnership, started publishing maps of ocean floor topography. So that partnership began using photographic data to locate downed aircraft from World War II, and they used that sort of experience to start mapping the topography of the oceans. And it was quite a partnership. You know, Bruce Hazing used to go offshore collecting the data, and Marie Tharp was working back in the office producing maps, because of course at that point women weren't allowed to go offshore. She didn't go offshore until 1965. So this first map was published in 1957 of the North Atlantic, and it was the first time that the complexity of the ocean floor is really revealed. It raised a lot of questions at the time. What was happening at this huge mountain range going up the middle of the Atlantic? You know, is that where new crust is being created? You know, it was 200 years ago that James Hutton came up with the theory of the heat engine, what we now know is the sort of driving force behind movement of tectonic plates. And it was more than 100 years ago that Alfred Wegener suggested the idea of continental drift. So this early map, for the first time, really started to hint at some of the sort of global forces. But again, you know, it was only the 1950s, you know, it was still viewed as controversial at that time. So if we flash forward just 20 years, you know, we get to 1977, and we see that same team produce the first systematic map of the world's oceans. And this map, I mean, it does just sort of blow you away. I use this a lot in my lectures, you know, I hope I don't sort of scunner people off it, but I think this just is a brilliant map for 1977. And it contributed towards the general acceptance of plate tectonics, at the time still new. But it really revealed for the first time, you know, the global network of mid-ocean ridges where new crust is being made, subduction zones where crust is being destroyed or recycled, seamount chains, you know, that give a flavour for the movement of some of the tectonic plates over time. You know, in my opinion, a remarkable map, even by today's standards. You can even sort of view this in Google Earth. You can sort of switch it on as a historical layer in Google Earth. You should check it out if you haven't done so already. But around about the same time, multi-beam echo sounder was being developed by the US Navy and was put to commercial use in the late 1970s. So multi-beam echo sounder, for those that don't know, It's instead of taking sort of one point depth every so often, like you would with an echo sounder, you send out a fan of echoes, of pings of sound into the water column, and you cover more seabed that way, because by taking this sort of fan of information, you're creating a corridor of data, you're recording a corridor of data, and you go out and sort of effectively mow the lawn and get a really high resolution picture of water depths, and you create a digital elevation model from those data, so you can get a true impression as to what the shape of the seabed is. And just a couple of examples there. I mean, this is the sort of top right image is round about Orkney, so showing sort of a series of recessional moraines coming back in towards the sort of mainland in Orkney. And in the south there, what am I talking about? The bottom picture there is a little perspective view of Meteor Deep in the South Sandwich Trench. So looking at where we are today, the best available global compilation maps is sort of GEBCO, who released an update just a few months ago. But again, a bit like with the sort of Hazen and Tharp map in 1977, you're sort of led into a false sense of achievement. It looks covered. It looks like there's nothing left to explore. But if we start to look in detail behind the pretty picture, as researchers, you always question your sources. You can start to interrogate the data behind the grid that's shown, the sort of lovely sort of topographic image that you see there. So this is the source grid of the GEBCO dataset, showing bathymetric coverage. And again, at that scale, the world ocean appears much better covered with ship soundings than it actually is. But in actual fact, only 18% of all the grid cells, which are about 1,000 meters across, a kilometer across, only 18% have got a sort of depth control point. So it's worth sort of bearing that in mind. A lot of that information that goes into that map is derived from satellite altimetry information rather than acoustic surveys. So there's quite a big variation in the resolution of our mapping of the sea floor. So you've got the sort of broad scale picture, as well as these thin, smaller patches or corridors of higher resolution information. And if we remove all the sort of satellite data and the sort of single point source data, we're only left with the sort of high resolution multi-beam lines. You can see that there's an awful lot more sort of blank areas than you maybe sort of thought before. So the immense area occupied by the ocean makes a complete high resolution up-to-date map a long way off, but there are initiatives ongoing at the minute. Seabed 2030 is highly ambitious, and they're looking to map the seafloor globally by 2030. And I love the ambition of that project. And there's a lot of people and organizations and institutes on board to contribute data to that cause. So just to remember that the take-home message is that only 18% of the grid cells all over the world's oceans have got a sort of a decent depth control point in them. So 80% we could do a lot better in. So that being said, it might seem that I've just been sort of fairly disparaging of the global or regional data, which is predominantly satellite derived, as I said. But as a tool for research in the deep places in Earth, the regional picture is incredibly useful. And using these global bathymetric compilations, we can start to look at the broad seascape, and working across disciplines, we can start to explore some interesting questions. So the deepest part of our oceans, between 6,000 and full ocean depth, which is 11,000 meters deep, it's called the Hadal Zone, and it represents some of the most active and diverse marine habitat on Earth. Well, of course I would say that because I like to work there. But understanding the extent of the Hadal ecosystem is difficult for marine biologists because of the complexity of the seafloor geomorphology in these areas. And traditionally, sort of biological studies of Hadal species, so the sort of fauna that live in water depths exceeding 6,000 meters, It's tended to focus on the conspicuous subduction zones, but these form sort of fragmented, geographically isolated, sort of almost inverted islands from a sort of biological perspective, if you will. So at great depths, the presence of features such as fracture zones and basins in between these subduction zones become more important. But at the minute, they're pretty much overlooked by Hadal scientists. So I'll just walk you through a quick sort of regional case study using some of the sort of broad scale data sets that I've been involved in recently. If we focus in on the Northwest Pacific Ocean, where the majority of Hadal features are located, we can evaluate the true extent of the Hadal ecosystem just using a sort of global, broad scale bathymetric data set. And I mean, you can see straight away that there's some obvious subduction zones. We've got Palau, Yap, Mariana, Volcano, Japan, Isobonan, Aleutian, Philippines. It's pretty obvious, they form these sort of linear arcuate subduction zones that are quite conspicuous in any sort of broad scale map that's produced. But just employing some basic morphological mapping, we can calculate the area that the Hadal zone of these trenches occupies, and it comes to about sort of 686,000 square kilometres. But if we delve just a little bit deeper, we discover that there's basins and fracture zones spotted all across the oceanic plates, away from the actual sort of subduction zone itself, and that increases the total Hadal area for a factor of 4. So just under sort of 3 million square kilometres, considerably larger, than that of the sort of subduction zones alone. So in addition to that, so we've not only just sort of increased our Hadal ecosystem, 4 times, we need biologists are interested in connectivity between these different areas. So previously, most people thought that the Mariana Trench, for example, this sort of arcuate trench here and on the right-hand side, left-hand side even, it was thought to be one continuous Hadal habitat. And the regional data, much of it again derived from satellites, as I've been saying, it reveals that the Mariana Trench is in fact 5 isolated areas separated by sort of biological, sort of geomorphological barriers that a Hadal species that's constrained to water depths more than 6,000 meters can't get across. So the most northern of those isolated areas is what Russians used to call the Volcano Trench. But I mean, as I said, this is important as one of the main characteristics of Hadal ecosystems is that there's a high degree of species endemism. So that's thought to be a result of physical isolation driven by, the geomorphological complexity, the geology, and also the sort of increased seismic activity that you get in subduction zones compared to the surrounding abyssal plains. So there's other factors influencing the sort of Hadal species as well, hydrostatic pressure and reduced food supply as well. But I mean, if we just focus for the purposes of this talk and on the geomorphology here. So in the most recent studies, the 2 main organisms that they use to study Hadal endemism are amphipods and fish. So the sort of fish species there are snailfish, and they are the sort of deepest, they're the only fish that have managed to get down to beyond 8,000 meters water depth. So amphipods are typically collected in large numbers using baited traps, while the fish are more often observed on the camera systems that we deploy to these sort of places. So, so the current theories sort of suggest that most amphipods and the fish can't, they form isolated populations that can't cross these abyssal level, these shallow water partitions that exist between, for example, here, the Mariana Trench and the Volcano Trench. You've got these sort of 4 partitions separating these into 5 distinct areas. Yeah, sort of Conversely, so same study, we can see that there's actually no physical partition so there's no boundary to biology. Life will find a way between sort of Japan Trench, Kuril-Kamchatka, Isobonin. They just form one continuous hadal ecosystem, one continuous corridor that, you know, you can have species can then travel from Russia to offshore the Northern Mariana Islands without any sort of trouble. So there's no biologically significant shallow water divide. And surprisingly enough, even just using this sort of broad data set, nobody had thought about that before. So that some of the biologist groups that are working at these water depths hadn't looked at that. They had thought that these trench systems were isolated from each other. And so when they were starting to look at their gene flow studies and connectivity studies, they were getting some interesting results that they couldn't quite tally with what they'd sort of gone into the study thinking. So there's quite a bit that we can start to unpick with a regional perspective, but we can also now, using sort of various technology and modern techniques, what do we start to see when we start to look in more detail? So Graham mentioned the Five Deeps expedition. I'll just take you through a few aspects of the Five Deeps. I won't take you on the full sort of 10-month tour. The Five Deeps was driven by a Texan called Victor Vescovo, and he came up with the idea after completing the Explorer's Grand Slam, which is climbing the 7 highest peaks on the 7 continents, and he became the 12th American to do that. And he'd also done the last degree, which is to ski the last 100 kilometers to the North and South Pole. So he's obviously quite an ambitious, adventurous type. And after he'd sort of done that, he was kind of left sort of sat at home wondering what to do next. So his attention had turned to the oceans. He was a former US Navy officer. So he wanted to become the first person to dive solo to the deepest places in the 5 oceans. So as researchers, you know, that isn't usually how we come to an expedition. You know, he's already got his goal that he's wanting to achieve. So we were kind of, you know, adding the sort of science on as we went. But ahead of the expedition, we published a desk study exploring, you know, just where the 5 Deeps are, and looking at the published bathymetry data, old records from vessels, you know, spanning the 19th, 20th and 21st century. We came across issues with naming conventions and all sorts, not just the resolution of the data, which in places was really, really bad. I realise I'm not skipping ahead in the pictures there. So areas like the Pacific and the Atlantic, the deepest points are pretty well constrained. You know, people have been heading into these areas for a long time. For a long time, people thought that the deepest point on Earth was horizon deep in the Tonga Trench. And the recorded depths between the sort of Mariana Trench and the Tonga Trench were actually pretty close, within sort of 100 meters or so. So, you know, that's within the sort of error margin of some data systems as well. So, I mean, it was worth sort of having a little bit more of a look at both of those trench systems. Again, in the Indian Ocean, there was a bit of a question. It was a toss-up between the Java Trench or the Diamantino Fracture Zone, which is off the southwest coast of Australia. And there's also an issue as to where the boundary of some of these oceans starts. You know, if you talk to different disciplines, where does the Southern Ocean start? Oceanographers will say somewhere different to the policymakers, say something different to the biologists. You know, so it's you know, getting to sort of unpicking some of those little sort of territories that we all put up round about our own areas of interest was an interesting prospect. So as well as sort of just trying to find a sort of route to go around the world and find the 5 Deeps, there was the issue that there wasn't actually a mechanism to get Victor down there. There wasn't a submarine, a full ocean depth rated submarine in existence. So that was a bit of a problem to overcome. So if we take a quick step back in time, the first time that Challenger Deep was visited was by John Walsh and Jacques Picard, who went down in the bathyscaphe Trieste 50 years ago. And the descent into Challenger Deep took nearly 5 hours. And once they reached the sea floor, Walsh and Picard, they observed their surroundings, but they couldn't maneuver. It was a strictly up and down job. So they only spent sort of 20 minutes on the sea floor. And their journey back up, so once they dropped their weights, they became positively buoyant, and their journey up only took sort of 3 hours and 15 minutes. So just so you know, Don Walsh is still going strong. I met him a couple of times now. He joined us on the 5 Deeps expedition for our Mariana expedition back in May and 2019. So that was good fun. He's a really interesting guy to get chatting to. But since then, only ROVs had made it down to the bottom of Challenger Deep. So it was sort of 40 years. And then James Cameron came along in 2012 with his Deep Sea Challenger. So Deep Sea Challenger, you can see it's a very different shape to the Trieste, which Walsh and Picard used. It looks a bit like a pencil, so that's to maximize your speed as you're going up and down through the water column. So they undertook a total of 5 submersible dives in Deep Sea Challenger. They did ones at sort of bathyl level, so just short of 1,000 meters, abyssal depths, just short of 4,000 meters. And they also did a Hadal test run in the New Britain Trench, and they went down to sort of just over 8,000 meters there. And they did a lot of observations for science, and that has been published in Deep Sea Research. And so Cameron went up and down very fast. It only took him sort of 2.5 hours to get down, but he maximized his time on the seafloor making these observations for science, spent 3 hours on the seafloor. But unfortunately, when Victor came along, previous to that, James Cameron had generously donated the Deep Sea Challenger to science, but unfortunately it caught fire when it was being transported to Woods Hole in the States. It caught fire in the back of a lorry and has been lost forever, unfortunately. So Victor went to Triton Submarines and got them to build a full ocean depth submersible for them. The link in the top right there, they've done a little video to show how they forged the sphere. So the titanium sphere is where the passengers and the passenger and the pilot are housed. So check out the documentary if you've got time and you're interested. It's pretty cool. But these slides are from John Ramsey, who actually designed the submersible. So the sort of section there with the sort of teeth going along the top, that's your titanium sphere. You can see the 2 comfy seats in the middle there. Those teeth are actually your oxygen supply, so that's your air supply whenever you're going up and down and taking part in a submersible dive. Only essential electronics and things are housed in the titanium sphere. Everything else is external so that it can be jettisoned if it needs to be. It's weight that can be lost in an emergency so that you can facilitate a quick return to the sea surface. But everything is attached to a sort of titanium frame, including, you've got your weights, which allow you to sink fast through the water column. You drop some weights while you're on the seabed to maintain sort of neutral buoyancy so that you can then sort of fly just above the seafloor surface, so you're not stirring up silt and sediments and things and clouding your view. And then of course you drop your excess weights so that you can come back up to the sea surface. Your batteries as well, they can all be ejected if need be. Across the top you've got sonar and communications equipment, and the exit trunk is about the height of me, so that's about, I don't know what, 1.8 meters high there, and you've got one of those classic sort of that you see in movies. So the hatch does actually have one of those round handles that you sort of crank and stuff, which is quite cool. The side view, you can start to see that it's got a sort of teardrop shape. And again, that just like James Cameron, that's so that you can go fast up and down through the water column. And we've got thrusters on the sides there so that we can maneuver once we're on the seafloor. We've got a manipulator arm to take samples and stuff. And then everything is just encased in your syntactic foam, which is your buoyancy for coming back up to the surface. So I'll sort of whistle through this. We also have a suite of scientific landers which record video, take samples. They've got baited traps for fauna and stuff down there. But they're used for navigation and communications for the submarine as well. And we did all this using a vessel, but I mean, relevant to this presentation is that we kitted it out with one of the new sort of deep water multi-beam systems, so that I could get, my research is based very much on multi-beam data. And I was very, very insistent at the start that you needed a multi-beam system so that we could properly map these areas. And also it's an opportunity that during these long transits between sites, we could just leave the multi-beam system running. And it means that we could gather more data to help fill in these gaps in the maps and contribute it to initiatives like Seabed 2030. So I'll just cherry pick a couple of highlights from that and some of the science that's coming out of that work. Hang on, quick check on time. I feel like I'm waffling on. So the Southern Ocean, indulge me for a moment. There's some nice pictures, but I mean, it was truly amazing. We were incredibly lucky that when we got to South Georgia, it was the first time that the rain had stopped in 6 weeks, according to the scientists that we bumped into down there at the base. It is just spectacular. I've been lucky enough to be down there a couple of times now, and it's just, yeah, blows you away if you ever get the opportunity to head down south, or you've been. Yeah, lucky you. And these are all, yeah, it was just one of those moments where you realise that you're sitting in the middle of a David Attenborough documentary, and there's sort of whales and penguins and icebergs, and that isn't even the largest one that we came across. And yeah, just fantastic. But back to the point, the South Sandwich Trench is a large arcuate trench spanning the South Atlantic and the Southern Oceans. As I said, it was discovered in 1926, and if you've received your copy of Edinburgh Geologist, there's a little bit of a potted history about exploration of the South Sandwich Trench in there. And hang on, what am I trying to see here? Yeah, so it's actually part of one of the largest marine protected areas in the world. It covers over 1 million square kilometres, and it was identified during a recent evaluation of that marine protected area that there was a significant knowledge gap from the sort of deep water areas of the marine protected area. So we were incredibly lucky that the South Sandwich Trench was on the hit list for 5 deeps, so we could we were lucky enough to get a grant from the Darwin Initiative so that we could work up the data from the 5 deeps in order to feed that back into the marine protected area governing bodies and to try and help them get much needed data from this ultra deep sea area to help support the existing MPA. So that's this grant is ongoing just now. It finishes later on this year. So we're working with the South Georgia and South Shetland Islands, not South Shetland, South Georgia and South Sandwich Islands government to make sure that we can get the information to them in a file format and a way that is best suited for their purposes, their management purposes. But so for the first time, we managed to acquire high resolution mapping along the entire trench axis. The deepest point in the Southern Ocean is one of these enclosed basins at the very southern end of the trench. And the enclosed basin itself is formed by a sort of complex interplay of the fabric of the incoming plate and bend-related faulting. So you get faults that are reactivated as the plate is being forced underneath the Scotia plate to the west there. But the deepest point overall is Meteor Deep, which we measured to be 8,265 meters deep. And, you know, well, the Germans got it right in 1926. They measured it as 8,264 meters deep. So, yeah, I mean, German efficiency and you know, 3 cheers for early echo sounding technology, because they were bang on the money. We couldn't have improved on that depth. So the completely previously unknown seafloor morphology of the South Sandwich Trench was revealed. We get a lot of these bend-related faults, which are highlighted by the little sort of yellow wriggly worms on the right-hand image there. And these bend-related faults form these large escarpments or cliffs on the seabed, and they not only sort of form distinct features in their own right, they can also transect and break apart seamounts, for example, that are being actively sort of taken and transported into the trench axis. But I mean, they're hundreds of meters high, and these sort of features just couldn't have been resolved using the existing sort of satellite-derived broad-scale bathymetry. We identified, you know, over 100 seamounts using the data, where only 2 were previously known. And seamounts are important for, you know, as biodiversity hotspots. They're important in terms of ocean currents and ocean mixing. Yeah, so I mean, the sort of 5 deeps has enabled us to sort of better map and better understand the dynamics of the sort of subducting interface in the South Sandwich Trench, feed that into policymakers as well. And we can also use that, and we can share that information. We're sharing it just now. We're trying to use sort of open source sort of web GIS platforms used by the Antarctic sort of family of organizations, to make sure that that information is available for future sampling campaigns. For example, a lot of biogeochemical and geomicrobiology trips that are ongoing just now, they want to actively avoid some of these seamounts and the bend-related faulting. They're looking for these soft sedimented sedimentary basins, you know, and we are in a position now that we can make that data available so that they can better plan their expeditions and not just go in blind. So if we just sort of skip over now to the Java Trench in the Indian Ocean, and a bit like the South Sandwich Trench, there was surprisingly little data available for the area. And even the sort of database of marine geographic features plots, you know, like the Java Deep, actually, you know, on the arc rather than in the sort of deep part of the trench axis. So we went there, and the deepest point of the Java Trench wasn't where I thought it was going to be, which was a bit of a blow. But nestled just between this incoming seamount in the middle in Box Sea, this incoming seamount and the forearc there, and the overriding plate even. So but I think, you know, we managed to get a lot more sort of science out of Java Trench, you know, not only from the multibeam, which I'll go into in a little bit more detail shortly, but also in terms of we managed to get a purely dedicated sort of submarine dive that was only looking at the science as well, and I'll show you some images from that too. Hopefully that'll run. So the topography of the Java Trench is just fantastic. I've got an active project just now mapping this. Again, we've got these large fault escarpments up to sort of 500 meters high, which also sort of cut the sort of subducting seamounts. So seamounts, again, as I said, are quite important, but they've got quite a large influence on the sort of process of subduction and deformation within the subduction zone plate interface. So even just getting a handle on where these seamounts are that are within the trench axis is interesting. But what has really sort of got me going is that once you get your eye in, you start to see all these little sort of cauliflower shapes or flower shapes. And these are just, there are a lot, you know, there's in excess of sort of 20 submarine landslide escarpments along this margin. And And these will have been triggered either through loading and gravity, but they may indeed have been triggered by earthquakes. And this is a region that has gained notoriety for devastating tsunamis. So it's important to say that not all landslides produce tsunamis, just like not every earthquake does. But these data give us an opportunity to study whether any of these past landslides had the potential to have generated tsunamis. Can we get a handle on how frequently these landslides occur? Can we narrow down sections of the margin that are more prone to landslides than others? Can we start to look at risk and working with sort of social scientists and local governments and things to explore that a bit more? If we sort of look a bit more at the seamount, we've got a, whoop, skipped ahead, go back. We've got a sort of head wall of an escarpment there. Hang on. And that headscarp itself is over 200 meters high, and it's almost 5 kilometers sort of wide. And we have run some preliminary sort of tsunami modeling on that. I mean, there's a lot of constraints that we need to sort of feed in and help better sort of tie down. But that one feature on that seamount, according to the tsunami modeling, the initial runs that we've done had the potential to impact the entire Indian Ocean basin with a significant tsunami. So again, chronology is a big question right now, but I mean, these are all things that we're starting to look into, and we would never have known that any of this was here without efforts and initiatives such as the 5 Deeps. So just having a look at some of the images here. I mean, there's lots of interesting sort of biology. That's the deepest octopus ever found. There's the one in the bottom right there is a stalked ascidian that is normally sort of attached to the seafloor, but we were reviewing the video, and this guy just sort of floated across the front of the camera. He'd obviously become detached, and he's being carried along in a oceanic current, just right in front of our lander, which was incredibly lucky. But the other seafloor images there are all taken from the submarine. And what I'm interested in, and we're hopefully going to submit a paper on this just in the next couple of weeks, is looking at if you sort of get your eye in, you can see that some of these surfaces look very jagged. And the sort of jaggedness is from these sort of escarpments, these near vertical escarpments. They're formed from the intersecting joints and the intersecting sort of joint planes, which once they sort of interact there, they create the opportunity, these planes of weakness for sort of really quite rectilinear angular blocks to just spall off these escarpments. And so you get small accumulations of sort of scree or rockfall deposits at the bottom of these escarpments. I mean, these are interesting for a couple of reasons. If you look carefully at the images there, you can see the bright oranges and bright yellows and the bright white colours. And these, we think, we don't have a physical sample, but by comparing to other sites around the world, these look like they're chemosynthetic bacterial mats, and they're exploiting, they're living off fluid circulation that's exploiting these planes of weaknesses, these joint patterns and joint surfaces within these escarpments. And it's worth noticing, it's worth mentioning even, and I should have done it before, is that this science dive was up one of these bend-related fault escarpments. So in terms of, I mean, it's interesting in terms of fluid flow, local fluid flow within the crust, fluid migration, but also in terms of the sort of the biologists that I'm working with, they're interested in terms of how stable these environments are, how stable the escarpment faces are, and potential recovery times for disturbed habitats. And these are just a few sort of highlights from other sort of sites that we visited. So we've got Java again. In Tonga Trench, again, we found more of the sort of chemosynthetic bacterial mats, but we were lucky enough, or unlucky enough, depending on how you look at it, to fly over the toe of a really quite large submarine landslide that we're still trying to sort of get to grips with. In the Mariana Trench in the bottom left there, that's Sirena Deep, and again, more of these chemosynthetic deposits. I'm beginning to wonder whether, you know, people always focus in on chemosynthetic sort of communities and stuff. We're finding them everywhere. Are they really all that special? Something to just throw out there. I find them quite cool because they're very colourful. But, and again, in the bottom right there, we found just purely by accident a relic vent field. So we've got this sort of flange structure that's no longer active. It is in situ. And so this is at a depth which is about the same sort of depth as the Shinkai vent field in the Mariana Trench. The difference here is that we're at this location in the bottom right-hand corner there is at the bottom of a seamount, whereas the Shinkai seep field is on the sort of overriding plate, which is a bit more expected in terms of a setting as a vent field. Just sort of touch really briefly upon, because I realised earlier on today that I had put sediments as part of the title, and then I realised that I wasn't showing too many sort of nice sediments. We did a trip to the Kermadec Trench a few years ago, and although that those data are currently being worked up, they've taken a bit of a different shine at the minute. So I'm not sure if you were aware, but there was a number of earthquakes off New Zealand within the Kermadec Trench just a few weeks ago. And what we end up here with is that we have the baseline data against which we can measure change. So we went out in 2017. In 2020, there was a magnitude 7.4 earthquake just in that star there. But just 2 weeks ago, like I said, there were a number of earthquakes exceeding magnitude 7 in the vicinity of this sort of K3 and K4 sites. So we've got a really quite amazing opportunity to measure, to go back, hopefully, and collect cores to compare and contrast with the cores that we had before. So some of this analysis is quite new. I only received some of these images a few weeks ago. I'm working with colleagues over in Niwa in New Zealand. And basically we're looking at a series of cores from the trench axis, which record a record of previous mass movement deposits. And again, a bit like Java, some of these will be purely gravity induced, but some of them will, however, be triggered by earthquakes. And you can see a few of the sort of thin laminae in that core. But some of these turbidites are incredibly coarse-grained. But I mean, the take-home message is that we've got this snapshot in time before a large magnitude earthquake, and a number of those have occurred over the last 18 months, and against which we're hoping to compare, you know, the after cores. And we're really hoping that we've got, you know, a surprising opportunity that's just landed on our plate because, you know, we've been there relatively recently, to unpick the record of paleoseismicity in the Kermadec Trench, and a record of these really quite deep water turbidite flows. So hopefully we'll get the funding. We've got an application in just now, and I'll be able to hopefully come back in a few years' time and present the results, maybe if EGS will have me back in the future. I realise that time's sort of wearing on, but you can't help but when you go off on all these multidisciplinary cruises, you know, the biologist starts to rub off on you a little bit. So we did over 100 lander deployments over those sort of 10 months, and there was a lot of firsts, a lot of data to add to the body of data from other trenches. But we discovered, you know, the deepest shrimp in I think it was the San Cristobal Trench, the deepest jellyfish, deepest siphonophore, first hazel larvaceans, and a lot of that work is being actively written up and published just now. Also, inevitably, this is hot off the press. This was just published last week. We just got this out. We did find trash. I tried to be optimistic and upbeat, you know, and I'm an incredibly excitable person anyway. But, you know, I try to look into positives, but, you know, sometimes you just can't help but sort of see the terrible things that we can do. So exploration vehicles can introduce vast quantities of single-use plastic-coated tether, which have basically the design of some of these vehicles, they deliberately discard their tethers at the end of their dive cycle. And we've started to see these at the deepest place on Earth in Challenger Deep. So these are images that were taken from the submersible vehicle limiting factor in the Mariana Trench, and it's literally hundreds of meters of yellow and white tether just strewn across the seafloor. But I mean, due to its composition, these fiber optic tethers, they'll persist environmentally, but they form a significant risk to equipment and, you know, and life. You know, I mean, should an unmanned or manned craft become entangled? You know, so I mean, as a result of this practice, you know, I think what we've thrown out in the paper is that, you know, we might have to put this area, you know, this iconic site of the first descent to the deepest place on Earth by Pickard and Walsh in 1960, we might have to put a big box round about it now and say, you know what, it's now too dangerous to go in there because you might get tangled up in these tethers that are just littering the seafloor. So a little bit sad. So yeah, I'll just I'm just sort of finishing up. Honestly, I am. I've been talking quite a long time, but I just wanted to share. I think a couple of you might have seen some of this already, but I did do something a little bit exciting in that as part of the 5 Deeps, I got a trip in the submarine. So I got to go down in the submarine with Victor. I got to go down in the Arctic Ocean, the Malloy Hole. Yeah, so it was unusual in the sort of 5 Deeps roster. It isn't a subduction trench. It's located on the Mid-Atlantic Ridge. And although it was the shallowest site we were visiting, you know, the biggest issue that we had was the weather window. Yeah, we were quite worried about there, but we managed to get there. The weather was good, and we had time for 3 dives at that location. Pardon me. So one was for the deep for Victor, but we managed to do 2 on the seamount, the sort of red blob there to the north, and that was interesting because the seamount is actually part of an oceanic core complex. So an oceanic core complex is a dome-shaped feature. Some describe them as looking a bit like a turtle shell, found on some mid-ocean spreading ridges, but only the ones that are spreading apart really slowly. So oceanic core complexes are interesting. They're used by research to look at things like understanding convection in the Earth's mantle, crustal processes, how ocean crust forms, and so on, ore deposits and the like. But what I find really interesting about oceanic core complexes is the potential of them hosting vent systems. And that's what we were looking for on our 2 dives. We didn't find any, but it was still totally awesome. So whenever you do a dive, you've got to put on a flame retardant suit. One size doesn't fit anyone at all, you know, but not the most flattering thing to wear. But we also had a documentary team on board the vessel, so there's an awful lot of, you know, how do you feel? Are you scared? You know, so you had to do lots of interviews and things. But I mean, I wasn't scared, and I think that's because I had got to know the people that built the submarine, designed the submarine, were maintaining the submarine. You know, I had absolute confidence in these people. I knew these people really, really well. So that there was at no point did I ever think, you know, oh, is this a bad idea? You can see the size of my grin there, so I'm just about to go in. So if you've got to sort of step off and onto the top of the submarine, sort of the guy in the wetsuit, the dry suit there is one of the engineers called Tim, and he's there for your safety, a bit like an air stewardess, except better, because he's also there to sort of seal you in and do all the safety checks and to detach you from the ship too. But of course, you know, as you're climbing in, everybody's then on the back deck going, Heather, Heather, look at me, yeah, smile, wave, woo. You've got to sort of sit there and do a little bit of a wave. So they then cast you adrift. Tim makes sure that you're safe and ready to go, and then you get your sort of authorization to descend. I actually ended up with 2 dives because we got to about 300 meters and there was a leak in the submarine, which I thought was normal. So there was this drip coming in the hatch and I thought that was fairly normal. I mean, we're in the ocean. I mean, surely, there's going to be a little bit of give, as things get tightened up under pressure as you're descending. And then Victor was like, no, that's not normal. We have to abort. But you know what? I was stoked because I'd got to 300 meters and it was an awesome experience. But the guys turned it around. It turned out to be a really small washer in the pressure release valve on the hatch. And 4 hours later, we were back in the submarine and heading down. And there's just a moment, a pure moment when the sea floor first emerges out of the gloom. You turn on your lights, the sonar is telling you that you're 100 meters off the seafloor, 80 meters off the seafloor. You start dropping some weights so that you're neutrally buoyant, and then you just start to see it. And it's just, a once in a lifetime opportunity and experience. And it was just the best thing that I've ever done, apart from having my kids, of course. But okay, third best thing. And we were flying over this seamount, this oceanic core complex. It was incredibly complex topography. We were constantly having to look out for hazard avoidance, cliffs, changes in topography and things, But I mean, it was amazing. We've got all these sort of sea lilies or crinoids sort of encrusting the exposed sort of peridotites and stuff. Sponges, fish, you name it, it was there. I mean, it was just brilliant. And you can tell by the size of my grin, all the green lights are good. You don't want too many reds, but yeah, it was amazing. It was so cool. And then you come back up, you drop all your weights, you come back up to the sea surface and you bob around for a while. Luckily, I don't get seasick, so that's good. But yeah, you then call and you wait on your taxi to come and pick you up, and you can see the guys coming on pressure drop, and there's guys in the rib who will sort of deploy Tim again so that you can attach all the ropes and the strops for lifting you back on board the ship. And yeah, it was just absolutely amazing from beginning to end. So just to sort of finish off, and my grin didn't stop for about 3 days afterwards. I think I was annoying everybody on the boat. So it was just cool. The deepest places on Earth are not out of sight, out of mind. And new technologies are just allowing us to access and study these ultra deep areas. But I mean, the take home from that is not just for research purposes, as technology is improving, it's also exploration is going into these deep areas as well. And we need to, that is something that is going to be part of our lives moving forward. And we need to get a better handle on the baseline information from these areas. So we need to be able to undertake surveys and grassroots research in these areas to really sort of see what the baseline is before we can go in and measure what change is going to happen. Our relationship with the deepest places on Earth, it underpins everything on Earth, and I'm incredibly lucky that I've had a number of opportunities over the years to work in these areas. So I'll finish off because I realise I'm a bit over time. Thanks very much to everyone that it's never a one-shot wonder. That I work with a huge team, and everybody has contributed to the work that's gone into this presentation. So any questions? Thanks very much. Hope I've not lost too many of you along the way. Thanks very much.
That's great, Heather. Thank you very much indeed. That was fantastic. I'm sure everybody has enjoyed that. We'll just open things up to questions. Between us, Tom and Angus and myself, we'll keep an eye on, people can either raise their hand, ask a question, or just unmute themselves and fire away. Or if you want, you can enter questions into the chat box, and we'll try and keep an eye on everything. So first question, who is the first question?
Oh no.
Have we got something in the... Heather, while people are gathering themselves, I'll ask. I think you very possibly answered this question not long after I thought it up, to be honest. But I was struck by how the sort of detail, the superbly high resolution detail that you're getting of the deep marine landscape. Have you? It sounds like you're now getting to the stage where you've got certainly the opportunities to revisit areas, or in new data sets compared with relatively recent and therefore still reasonably high resolution data sets. Are you getting the chance to really see the sort of scale of landscape change that there is, or there might be, associated with big earthquake events or sizable earthquake events? I imagine these things are very destructive, and there must be quite wholesale change to the seabed landscape. Have we got any indication of that?
The projects that I've been on, I mean, we're hoping to get back out to do some of these repeat surveys. So that's kind of on the cards, and we've got ship time applications and things in progress. But other research groups have, you know, I mean, classic cases, of course, the Japanese event in 2011.
Yeah.
So researchers there had really quite high resolution data sets from before the event, and then they could get out there very rapidly and acquire new data to see where exactly the movements had come from. And that's well published now. There's a lot of information. I mean, what's interesting, I mean, I spoke before about the impact to the habitat. So a lot of these hadal fauna, they're incredibly sort of slow growing. It takes them a long time to get sexual maturity as well, for example. And it's how destructive some of these events are. And his name has just completely escaped me. That's terrible. I've been offshore with him. Oh, anyway, a Japanese collaborator I have been working with, he published out a really lovely paper. Well, lovely in that it was lovely science rather than the message it was sending home. But it was the length of time it took for the disturbed sediments to settle out in these deep water areas. And he was just sort of recording literally like carcasses of fauna, not only fauna that had been taken in from the sort of shallower reaches, but the endemic hadal fauna as well. So yeah, I mean, we're really pinning a lot of hopes on the sort of grant application to get back out to Kermadec, because I think that's a really great opportunity that we've got the before snapshot in time, rather fortuitously, and you know, we're really hoping that we'll get back out and get the after, and that'll be in collaboration with NIWA and our colleagues in Denmark and in Germany.
Excellent, excellent. Let me look through here. Christine Thompson asks, what adaptations do the animals that you see have to the pressures that you're finding them under? Right,
okay. I do know this, but it's terrible. But okay, so the one of the bigger things is that there's a enzyme called TMAO, and I do have it written down somewhere, but I can never remember what it is. But basically, it exists within the cells, and it helps sort of push out against the water pressure pushing down. And so, but it's an osmolyte, sorry, not an enzyme, it's an osmolyte. But there is a maximum level of that, and it's around about, I think, 8,500 meters water depth. So beyond that, you cannot get any fish. So the best adapted sort of things are things like your holothurians and your sea cucumbers and your amphipods. And so they're really well adapted for full ocean depth. I mean, you get them down at, you know, the deepest points, but you only get fish down to I think it's about 8,500 meters, because they're reliant on this osmolyte TMAO to help to stop their cells basically just being crushed by the water pressure.
Okay. Here's one that it's probably one you don't want to think about when you're in the submarine. Jim Martin asks, if you have a technical problem at depth, what recovery options are possible? He assumes that the submersible is untethered, but it has some sort of automatic return protocol or whatever. How does it work?
Yeah, so there are a few things. And it is something that you do think about, you know, for obvious reasons. But yeah, so there's a few things. So there's, I think it's called dead man calling or something. So every 15 minutes, you've got to radio in and say, you know, you give your, you know, what level your life support systems are, you know, comms good, if there's any issues, whatever. If you miss 2 of those, then it's automatic, you know, even if you just accidentally missed it, it's automatic. You'll drop your weights and you'll go back up. Yeah. So regardless, like journey over, right? So that's one. The other thing is that, I mean, if something was to happen, if you remember, I said, you know, so you've got your titanium sphere, but it's only sort of essential stuff that's in there. Everything else is external and everything can be jettisoned, which would then mean, so, and it can be jettisoned sort of manually. It's not just, you know, there's like sort of manual kind of clips that you can do. It's not just, you know, electronics and things. If that happens, you know, you can jettison everything, especially batteries. Batteries are heavy, and you'll float back up. The issue there, I mean, you will float back up and you'll be okay. The issue is that it's an uncontrolled ascent, so it will be rough and you'll probably be sick. Yep. But I mean, you know, you've got enough oxygen for, you know, like 96 hours, even though, I mean, realistically, you wouldn't do a dive cycle longer than about sort of 16 or something. You know, you've got oxygen, carbon dioxide scrubbers and things. You know, there's, you know, fire safety equipment down there as well with you. So, and you before you, even as a passenger, you've got to sort of be familiar with all of that, because I mean, your pilot could become incapacitated or something, so you need to know how to at least press a few buttons so that you can get back up safely.
There's one here, Heather, from is it Jay Robson? I'm not sure who Jay is, but is Jay around? Would they like to ask their own question, or shall I just go ahead? No response. Anyway, Jay Robson asks, and it did occur to me, Heather, you pointed out the litter and so on that you're finding on the in these deepest parts of the oceans, and I think we've all seen similar things. But then you did mention that for your return journey, you drop weights, and kind of how does that balance against the litter that you discover when you go down there in the first place?
Yeah, it is a really good point. I suppose there's an element of environmental impact. You know, the sort of weights that we are dropping, they're, you know, they sound like, you know, there should be loads of them, but they're relatively small. They're also made of, you know, it's just bog standard iron, and it will relatively quickly just rust into nothing.
Right.
So in terms of your environmental impact, it's relatively low. What is sad is that, you know, we have seen like loads of plastic. The guys that I'm working with at Newcastle, you know, they described a new species from Mariana, and it was brand new to science. Nobody'd ever caught it before, and it already had microplastics in its guts. Yeah. So, you know, it's stuff like that. I mean, you know, there's persistent things, you know, there's documented evidence of, you know, persistent organic pollutants within the tissues of some of these animals. Flame retardants, you know, that are now, you know, that were banned in the 80s, you know, they're found within some of these animals and tissues and things. So, I mean, I'm an optimist, and I like to try and focus on the sort of happy, you know, isn't this all sort of, you know, exploration and sort of a bit of blue skies about it? Isn't this all wonderful? But the sad fact is that you see it all the time. Yeah. You know, Puerto Rico Trench is, you know, we were finding like 8,000 meters water depth, and there's like Heineken cans. Oh God! You know, it's you know, is that, you know, at least make it a decent beer if you're going to dump your can. Yeah,
we leave a lot to be desired sometimes, don't we? There's a question here from Bob Gatliff, and I can see Bob there, so Bob can unmute himself and ask his own question. Bob, how about that?
Oh gosh, my boss, my old boss.
No longer, Heather. No longer. Well retired. Yeah. Now, a couple of points. Oh. I can't remember what I wrote now. First of all, you use the EM124 multi-beam from the surface, but you know, if you'd used a deep water ROV, would you get much better resolution?
Yes, of course. I mean, I think I meant to mention it, but I obviously didn't. You know, for those that don't know, if you use something like a autonomous underwater vehicle or an ROV, you can attach a small multi-beam system to these vehicles and acquire data, you know, that's like centimeter resolution rather than tens of meters or meters. The issue there is actually some of those, well, one, you know, I think the Chinese now have trialed a full ocean depth AUV, and there's full ocean depth ROVs, but having a multi-beam system that is also full ocean depth, that is within the weight capabilities of some of these, like ROVs, for example, is an issue. So weight is always, and pressurizing some of these systems is always an issue. But it's just time. So if you want to go and visit some of these places, I mean, if you're going to sit and try an ROV, you know, like a rock face, and use an ROV to survey that rock face, that would be fantastic. But the survey effort and the cost of your vessel sitting on station to do that is huge. I mean, it's just, and what are the questions that you'd be trying to achieve? Whereas, you know, shipborne multi-beam, I mean, yes, that EM124 wasn't cheap by any means, but once it's on, you can just go out and mow the grass and just, you know, bish bash bosh, you know, a week's, I mean, South Sandwich Trench took us a week survey.
Can I just ask one more about, you know, when the Malaysian aircraft was lost?
Yeah,
the Australians did quite a lot of multi-beam. I didn't see it on your map of the latest coverage. Is it just because it's such a small area compared with what we've got that it just doesn't make a dent in our understanding?
You mean the sort of JEBCO outline?
Yeah. Yeah,
it maybe just didn't show up in terms of scale. But I mean, yeah, that work, you know, led by Kim Pickard at Geoscience Australia. She's a friend to BGS. Yeah, it's a very sad reason about the reasons behind why they had to go out and acquire that data, but the actual sort of data itself is amazing, and the knowledge that they're gaining as to, you know, the interactions between the Antarctic plate and the Indian Ocean plate, for example, the fracture zone itself, you know, the extension of the Diamantina fracture zone and stuff is, you know, it's really, really nice science coming out of that. Yeah. I'm not sure why it didn't sort of show up. I think it was just an issue of scale rather than it not being there. It has been submitted to Seabed 2030.
Can I ask one more question?
Go on then, Bob.
When I was working, I really tried to push the British government to do multi-beam surveys of the whole of the UK CS, so that we could really underpin what we've got, both geologically and biologically, and habitats, and we've still not managed to complete it all. Is that something that the Scottish Geology Trust should push the Scottish government to complete?
Yes, keep me in a job.
Right answer.
Yeah.
Thanks.
Absolutely.
I'll give the last question and give Heather a rest. I'll give the last question to Stephen Davidson. I see Stephen there as well. So if Stephen would like to unmute himself and ask his question. There you go, Stephen.
Hi, Stephen.
Yeah. The image you had right at the beginning of your talk on the moraines from Orkney, is that a published image or is that still work in progress?
No, well, it's published by a couple of folk. I can send you I've still got the same BGS email, so ping me an email,
yeah, okay.
And I can send you the references. Tom Bradwell published that in 2019. It's data acquired by the Marine and Coast Guard Agency, and then I've just had it accepted for a book chapter looking at the geomorphology of the continental shelf of Scotland.
Okay.
Yeah. So it's been published a couple of times, but it's open access data. Anybody can look at it through the Admiralty data website.
Right, okay, cheers.
Right, Heather, I think there may be one or two questions I've missed in the chat. There were quite a few coming in, but we kind of hang around afterwards for the vote of thanks, and maybe there'll be a little bit more informal chat in a moment or two. Unfortunately, we can't treat you to a cup of tea upstairs, but that's the way these things go. I'm going to hand over, oh, well done. I'm going to hand over now to Tom to do the vote of thanks. And my point of view, Heather, it's been great. Thank you very much.
Thank you very much for having me. Yeah.
Right. Thanks, Graham, for fielding all those questions. So I really hope that everybody present tonight understands how privileged we have been to basically get a glimpse of the last frontier on planet Earth. In that respect, this is absolutely cutting edge science. And I'm reminded of the Perseverance rover that's just landed on Mars. And what we see, what we've seen here tonight is on par with that, really. I mean, the amount of data that we've got of Mars, I mean, all of Mars has been basically mapped. The surface is mapped, and we haven't got that for the deep sea. So I think the only way in which it might be slightly different is it's probably slightly cheaper to get to the bottom of the sea, and you can more easily get a few samples back. So, but the parallels there are certainly very, very strong indeed. So we're looking at, we've seen science this evening that is on par with going to Mars, and I think we're extremely privileged to have seen that. But also, I think I'm amazed and extremely privileged to have actually met someone who's been down there in one of those fantastic submersibles. Heather, you kept that quiet. I never knew that about you. And that's absolutely fascinating. I mean, it also sort of shows how your work, you look at your work remotely using multi-beam data, but you've also been down there as well. So I imagine for you, that must sort of really nicely bring the two lines of your work together. But what we must understand about all the type of work that Heather is doing is how it really paints a picture, and it's at the forefront of our understanding, really, of what we see on our backyard. Let's take the southern uplands, for instance. It's an accretionary wedge. And Heather was showing us environments where accretionary wedges are forming today. So her work is absolutely important in our understanding of deep marine deposits that we see exhumed at the surface today. So we're extremely fortunate to have seen that as well. So Heather, thank you very much for sharing some of that data. I saw some of it was also in press still, which is really exciting because it's new stuff that's just about to come out, and it shows how cutting edge your work is. And I'd just like to finish by saying thank you for providing us with an absolutely fantastic last lecture in our lecture series. And once you've finished all the collecting data you mentioned, in a few years you come back. Yes, I think we should do that. You should come back, and hopefully you'll have had the opportunity to go down to the bottom of the sea again as well. So on behalf of everybody here tonight, thank you very, very much indeed. That was fantastic.
Great, Heather, thank you.